questions in the chat. If somebody has one.
Yes, so I've designed it to be slow paced, so you can essentially interrupt me at any times. So this talk is going to be an invitation to explore the role of kernel methods in learning and solving differential equations. Now, before I get into the main topic of this talk, I will give a short reminder on scalar-valued kernels to make sure that everyone is on the same page. I will do so in the setting of the following interpolation problem, in which you try to approximate an unknown target function, f dagger, mapping some input space x to the real line, given that f dagger of x is equal to y. Here I write x and y for the n-dimensional vectors, whose entries are the input-output data points, and I write f dagger of x for the n-dimensional vector, whose entries are the images of the input data points under f dagger. Now, there are 4 equivalent ways to describe kernel-based solutions to this problem, and these are based on the following 4 equivalent ways of defining such kernels. The first one is to define a scalar-valued kernel as a function k mapping the input space x times x onto the real line, such that for all integer m and all points x1, xm in the input space, the m by m matrix with the following entries is symmetric and positive. Now, equivalently, K is a scalar-valued kernel if and only if there exists a Hilbert space F, known as a feature space, and a function psi mapping X to F, known as a feature map, such that Kxx prime is equal to the inner product in the space F between psi at X and psi at X prime. Now, this is equivalent to the existence of a Hilbert space of functions F mapping the input space X to the real line such that f of x is equal to the inner product in the space H between f and the function defined by the kernel K supported at the point little x. The norm associated with the inner product in H is known as the RKHS norm associated with the kernel K, and we will also write it as this K norm for ease of presentation. Now, this is equivalent to the existence of a centered Gaussian process Xi, such that K is the covariance function of that Gaussian process. Recall that Xi is a function mapping X to a Gaussian space, okay, which is a Hilbert space of scalar-valued Gaussian random variable, and that the covariance function of Xi is the function obtained by computing the covariance between Xi at X and Xi at X prime for all X and X prime. Now, these 4 equivalent definitions lead to 4 equivalent solutions to our original interpolation problem. The first one is to approximate the target function f dagger with the following function f, where k is our given kernel, k of capital X is the n by n matrix with the following entries, and k of little x capital X is the n-dimensional vector with the following entries. The second one is to approximate the target function with the following inner product involving the feature map psi associated with the kernel K and some coefficient C living in the feature space F, identified by minimizing its norm subject to the interpolation constraints. Therefore, you can think of kernel interpolation, also known as Kriging, as a linear interpolation in feature space. And the main idea is to first map the data to a Hilbert space via possibly nonlinear feature map, and then to linearly approximate that target function in that feature space. The third one is to approximate the target function with the minimizer of the following problem, in which the norm to be minimized is the RKHS norm defined by the kernel K. Recall that since these methods are equivalent, this norm is also defining the kernel K. This approach is also known as optimal recovery in numerical approximation, and it can be traced back to the work of Micheli and Rivlin. The fourth one is to approximate the target function by the expectation of the Gaussian process with covariance function K, conditioned on the interpolation constraints. Okay. So why are kernel methods relevant to numerical approximation? Well, as observed by Sard, Larkin, Diaconis, and many others who have investigated intriguing similarities between Gaussian process regression and numerical approximation, most numerical approximation methods are actually kernel interpolation methods. For example, the cardinal splines of Schoenberg are optimal recovery splines, that is, kernel interpolants obtained from 0-1 measurements and defined by polynomial kernels. This is also true for the polyharmonic splines of Hardet, Demarais, and Duchamp, which can be identified as optimal recovery splines. To describe this, consider the problem of approximating the solution F dagger of the following PDE with an unknown right-hand side in L2. Assume that the values of F dagger are given at this n homogeneously distributed points xi of the domain omega, which I assume to be a subset of RD of dimension less or equal than 3. Then the polyharmonic spline approximation of F dagger can be identified as the minimizer of the following variational problem, which is an optimal recovery problem. So this minimizer F is a kernel interpolant with a kernel K defined by the following RKHS norm. Furthermore, this kernel interpolant is good in the sense that it achieves the minimax optimal rate of convergence in approximating F dagger given that the right-hand side is in L2, okay? This is also known as the Kolmogorov n width. So you can achieve the Kolmogorov n width up to a constant. Now, this doesn't mean that all kernel-based solutions are good. In fact, if you replace the Laplacian in the previous PDE by a divergence form elliptic operator with rough coefficients, then the convergence of the previous kernel-based method can be arbitrarily bad. Why is it so? This is because the kernel associated with this variational problem is not adapted to the underlying PDE or physics. So what is the solution? Well, it is simply to use a PDE-informed kernel, and this can be done by replacing the previous optimal recovery problem by the following one, in which the quantity to be minimized is the L2 norm of the right-hand side of the PDE. And then you achieve the Kolmogorov limit up to constant. Now, this solution is a Gaussian process regression solution with a PDE-informed prior. This PDE-informed prior is obtained by replacing the unknown right-hand side of the PDE with white noise and using the resulting Gaussian process on the solution space as a prior containing the needed information about the macrostructure of the underlying PDE. Now, this Gaussian process regression interpretation of numerical approximation is not just an object of curiosity. It can be used to discover state-of-the-art solvers, which I will not cover here. And it can be generalized to arbitrary nonlinear PDEs, which is something that I will cover now. Now, one motivation for this generalization is that there is currently a growing interest in using learning methods to solving PDEs. These methods can be divided into two categories: approaches based on artificial neural networks with physics-informed neural networks as a prototypical example, and approaches based on Gaussian processes with gamblets as a prototypical example. Although the Gaussian process approach is more theoretically well-funded and has a long history of interplays with numerical approximation, it was essentially limited to linear / quasi-linear / time-dependent PDEs. And the result that I will present now is the generalization of Gaussian process methods to arbitrary nonlinear PDEs. And what I'm going to describe now is a joint work with Yifan Chen, Bamdad Hosseini, and Andrew Schwartz. Now, the method that we have obtained from this generalization has several desirable properties. It is provably convergent for forward problems. It is interpretable and amenable to numerical analysis. It can be applied to solving both forward and inverse problems. It inherits the complexity, the computational complexity of state-of-the-art solvers for inverting dense kernel matrices. And its underlying framework could be used to develop a theoretical understanding of artificial neural network-based methods. Now, this Gaussian process method can be applied to arbitrary nonlinear PDEs, but for ease of presentation, I will describe it first for the following nonlinear elliptic PDE, in which f, g, and tau are continuous functions, such that this PDE has a unique, strong, or classical solution. So the nonlinearity in this PDE is tau, which we assume to be continuous. Then, given a kernel K, the proposed approach is to approximate the solution of the PDE with a function U minimizing the following nonlinear optimal recovery problem, in which the objective is the RKHS norm of the function U defined by the kernel K, and the constraints are requiring U to satisfy the PDE at a finite number of collocation points. Okay, note that some of these collocation points are in the interior of the domain and some are on the boundary. And note also that the PDE constraints at those collocation points depend on whether they are located in the interior of the domain or on the boundary. Then we have the following theorem. Assume that the kernel K is chosen so that the RKHS space, so that its RKHS space is contained in the sublet space HS for some S greater than the dimension of the space over 2 plus the order of the PDE, which is 2 here. We need that condition to ensure that the PDE can be defined pointwise for the elements of that RKHS. Assume that the solution of the PDE belongs to that RKHS. And assume that the field distance between collocation points goes to 0 as the number n of those points goes to infinity. Then as n goes to infinity, the approximation U identified by our method converges to the solution of the PDE, where the convergence holds pointwise and in the sublet space HT for all t smaller than s. So this theorem is essentially saying that the proposed method is guaranteed to converge as the collocation points become dense in the domain if the kernel K is adapted in the sense that the solution belongs to the RKHS space defined by the kernel K, and that space has enough regularity to be embedded in a sublet space containing functions with continuous second-order derivatives. Now, for the practical implementation of this method, this infinite dimensional variational problem can be reduced to a finite dimensional one by introducing the slack variables Z corresponding to the values of U and of its Laplacian at the collocation points, and then minimizing over U before minimizing over Z.
I'm sorry,
Now,
may I ask a naive question when I look at this? Yeah, just how do you compute the Laplacian if, for example, these collocation points are Monte Carlo samples. So how do you compute the Laplacian numerically in your examples?
So here you don't need to compute the Laplacian of U. If you want to approximate the solution, you only need to compute the Laplacian of the kernel, which is something that I'm going to show now.
Thank you.
There's also one other question in the chat, which says,
Yes.
what is the intuition behind choosing one or another functional in the minimization problem for the recovery?
Oh, can you repeat the question?
What is the intuition behind choosing one or another functional in the minimization problem for the recovery?
By functional, do you mean kernel or do you mean something else?
This I don't know. The L2 norm.
The L2 norm. So that was before, I guess. I think the question is referring to this slide where we chose the L2 norm of the right-hand side. In fact, you could also choose the energy norm of F, and this thing will also work, right? The intuition is essentially the prior assumption that you are making on the regularity of the right-hand side. If you assume that the right-hand side is in L2, in fact, you could just use the energy norm. If you assume it to be in something better than L2, you could use that or something more regular, right? So basically, the intuition here is the kind of assumption that you are making on the regularity of the right-hand side, which translates into the solution space with that right-hand side being compactly embedded in H1, right? Another way for me to say this is that the more regularity assumption you assume on the right-hand side, the faster rate of convergence you can get in your numerical approximation method. So if you assume the right-hand side to be analytic, for instance, and if you choose, if you replace G by a Gaussian process with a Gaussian kernel, you are going to get an analytic rate of convergence if instead of minimizing the L2 norm of the right-hand side, you minimize the RKHS norm of the right-hand side defined by the Gaussian kernel, okay? So it relates directly to the kind of regularity or integrability condition that you put on the right-hand side. And you need some, because if you only assume that the right-hand side in H-1, there is no way that you are going to get any convergent numerical method, because you need some compactness to get convergence. Does that answer the question?
Yes.
Okay. So let me go back to nonlinear PDE. So here, our problem is to turn this infinite dimensional variational problem to reduce it to a finite dimensional one. And the way we're going to do it is by introducing this slack variable z corresponding to the values of u and of its Laplacian at the collocation points, and then minimizing over u before minimizing over z. Now, observe that this minimization over u is a linear optimal recovery problem, for which we have the following representative formula involving those slack variables z, which are in turn identified by plugging in that u in that expression and minimizing the following optimization problem, which is quadratic in its loss and nonlinear in its constraints. Now observe that this optimization problem involves this kernel matrix K phi, which is defined or obtained by integrating the kernel K against these functions phi I and phi j. And these functions phi I and phi j are essentially concatenations of masses of Diracs located at collocation points and masses of Diracs located at collocation points composed with the Laplacian. So if you integrate this expression by parts, what you end up evaluating is the kernel K at the collocation points and the Laplace derivatives of the kernel K at collocation points, okay? So in practice, you're never going to directly take the Laplacian of some arbitrary function u. The only thing that you need to compute the Laplacian of is that kernel k. Okay. Now, to solve this reduced finite dimensional constraint optimization problem, we use the constraints to eliminate one of the optimization variables, which here is the vector z2, whose entries are the values of the Laplacian of u at the collocation points. And we turn this non-linearly constrained quadratic optimization problem into an unconstrained non-quadratic optimization problem. Now, to solve this unconstrained optimization problem, we simply use a variant of the Gauss-Newton iteration or algorithm. So this algorithm is an iterative algorithm obtained by successively linearizing the nonlinearity tau around the previous approximation of the solution. And this is what this linearization looks like. And then by solving a quadratic, this resulting quadratic optimization problem in the increment that to get the next approximation of the solution, which is this guy. Now, in practice, this Gaussian-Newton algorithm converges in 2 to 7 steps, which means that the complexity of our nonlinear PDE solver inherits the complexity of inverting dense kernel matrices. And we are currently adapting the algorithm found in this paper to do so in near-linear complexity. Now, this Gauss-Newton iteration is equivalent to solving successive linearization of the underlying PDE with that particularly selected kernel, which is equivalent to using Newton's iteration to solve the nonlinear PDE. And again, this is with that particular selected kernel. The following experiments compare the convergence of the finite difference method with the convergence of the proposed method using a Gaussian kernel. This is when the nonlinearity is 0, and this is when the nonlinearity is u cubed. And this is our Gaussian kernel. Now, as mentioned before, this method and its convergence theorem generalize to arbitrary nonlinear PDEs. And as an example, these figures illustrate the accuracy of the proposed method for Berger's equation when using the following anisotropic kernel, in which the length scale of space has been chosen to be smaller than the length scale of time to capture the underlying shock. Okay, and what I want you to observe is that you have a converging method, which is something very difficult to get if you are using an ANN-based method. These figures illustrate the accuracy of the method for Eichhorn's equation with a Gaussian kernel. And here our Gauss-Newton algorithm converges in 6 steps. Okay, and this table shows the convergence of the method as you refine the mesh, or as you decrease the field distance between collocation points. Now, this method can naturally be extended to inverse problems. And as an example, consider the problem of approximating the solution u and the coefficient a of the following PDE, given the values of u at a finite number of points, which are colored in pink in this figure. Then the proposed generalization is to simply recover the solution and the coefficient of the PDE by minimizing the sum of the square of the RKHS norms with respect to two possibly different kernels subject to the PDE being satisfied at a finite number of collocation points on the boundary and in the interior, and also subject to our measurement of the value of the solution at the data measurement points. And these figures show the true and recovered solution of the PDE and the true and recovered conductivity coefficient of the PDE. The underlying Gauss-Newton algorithm converges in 5 steps. Now, note that here we are solving both the forward and inverse problems at the same time, whereas the classical MCMC approach is to iterate between solving the PDE and solving the inverse problems. Furthermore, again, the complexity of the method inherits that of inverting dense kernel matrices, so near linear complexity, which is really fast for an inverse problem.
There's one question in the chat.
Yes.
And it says, it was about 2 minutes ago, interesting nonlinear elliptic PDEs are known to have multiple solutions. How do you know that the method is converging and to what?
So here, for that particular example, we assume the nonlinearity tau to be such that the PDE has a unique strong solution. So if you take tau to be u cube, tau of u to be u cube, this is the case. We make that assumption. Now, an interesting question is what happens if there is no unique strong solution? Well, what you are going to converge to is towards the minimizer of the RKHS norm. So you're going to converge towards the solution that is the most regular in the sense defined by the RKHS norm of the kernel that you have selected. Okay, so you can in fact apply this method for PDEs for which there is, if the right hand sides are continuous and if this thing is continuous, you can also apply this method for PDEs for which there is no continuous or strongly defined solution. So you get a new notion of solution that depends on the underlying kernel in those settings. And it's an interesting question to investigate how those notions of solution generalize the notion of the classical or weak notion of solution that we have for PDEs. Okay.
May I ask a question while we're on the Burgers equation?
Yes.
So are you so you're approximating the solution. So the function you're approximating here is the function which maps time and space to the scalars. So the initial data is fixed. So you always find a different map for different initial data. So basically you fix the initial data and then you approximate the solution, right?
Correct.
Okay, thank you.
You're welcome. And here we are finding the solution for all data points in space and time at the same time. You could also come up with a variant where you come up with an iterative solver where you solve forward in time. This is not what we have done here.
But for example, is the solver robust with respect to perturbations of the initial data?
Yes.
Thank you.
You're welcome. Okay, now in all these methods, we have to select a kernel K, and the performance of the method actually depends on the choice of the kernel K. So what I would like to describe now is a method for choosing the kernel, and what I'm going to describe can be found in the following 2 papers. The first one with Jin Ryan Yu, and the second one with Yifan Chen and Andrew Schwartz. I will describe this method in the setting of our original interpolation problem, where we want to approximate an unknown target function f dagger, mapping some domain D of Rd to the real line, based on observing the values of f dagger at n data points, x1, xn. I assume that we are given a family of kernels on the domain D, parameterized by some hierarchical parameter theta. So given theta, the kernel interpolant is then represented by the following formula. And the main question that we are going to address is, which theta do we pick? We are going to cover, to consider 2 possible answers to this question. The first one is known as the empirical bias answer. And this answer is to place a prior on theta assume that given theta, the target function is sampled from a centered Gaussian process distribution with covariance function k theta, then select the theta maximizing the marginal probability of theta subject to conditioning on the values of the target function at the data points. And if we use an uninformative prior on theta, then the resulting estimate is a maximum likelihood estimate obtained by minimizing the following loss function with respect to the value of theta. The second answer, which we refer to as the kernel flow answer, is a variant of cross-validation. And the main idea is to pick a theta such that subsampling the data does not influence the interpolant much. So formally, the kernel flow estimate of theta is obtained by minimizing the following loss with respect to theta. This loss is defined as a relative error between two interpolants. The first interpolant is the interpolant obtained with the kernel k theta and all the data x. The second interpolant is the interpolant obtained with the kernel k theta and a subset of the data pi x. So this operator pi is a subsampling operator and pi x is a subvector of x. And the norm used to define this relative error is the RKHS norm of the kernel k theta. So again, the main idea here is that the kernel is good if subsampling has little impact on the approximation of the target function, which is essentially a cross-validation idea in the sense that this relative error acts as a surrogate for the generalization relative error. So we have two natural methods for selecting theta, and a natural question is what is the behavior of these methods as the number of data points goes to infinity? Well, to answer that question, we're going to consider the following particular example in which the domain D is the unit torus of dimension D. The data points are located at the nodes of a regular lattice of resolution 2 to the power minus q. The kernel k theta is the Green's function of the fractional Laplacian with power theta with periodic boundary conditions. And our subsampling operator subsamples the point located on the coarser lattice of resolution indexed by q minus 1. Then we have the following theorem. If the target function is sampled from the distribution of a centered Gaussian process with covariance function ks with s greater than d over 2. So we assume the model to be well specified and the true theta to be s. Then as q goes to infinity, so as the number of data points goes to infinity, then the empirical bias estimate converges to s, and the kernel flow estimate converges to s minus d over 2, where the convergence is in probability. So an immediate question is, how are those two limits, s and s minus d over 2 special? Well, the short answer illustrated in these two experiments in which s is 2.5 and s minus d over 2 is 1, is that kernel flow selects the smallest theta achieving this fastest rate of convergence in mean square error, and empirical bias selects the theta minimizing the mean square error. One question that may be asked is why should anyone use kernel flows if empirical bias is optimal in mean square error? And the answer, which I don't have the time to cover here, is that the optimality of empirical bias assumes the model to be well specified, and empirical bias can be brittle, that is not robust to model misspecification. Whereas kernel flow has some degree of robustness to misspecification, and it is also nearly optimal if the model is well specified. And to illustrate this point, I will now consider an example where there is no obviously well-specified model. This example concerns an extrapolation problem in which, given the observation of the time series Z1, Z2 up to time n, we want to predict the future states Zn plus 1, Zn plus 2, etc. Evidently, to solve such a problem, you need to make some assumptions. And the assumption that we will make here is that the Zk can be obtained as the solution of some dynamical system with an unknown vector field f dagger and an unknown time delay tau dagger. As you can imagine, this is a fundamental problem which has received a large amount of attention from the perspective of some wonderful methods, ranging from operator theory, Houman, sparse approximation, manifold learning to various variants of artificial neural networks. And all I want to do here is to show you the simplest possible kernel-based solution you can imagine. And what I am going to show you can be found in the following paper with Houman Owhadi, which is in the audience. So this solution is to approximate the vector field F dagger with a kernel interpolant, and then use that kernel interpolant as an emulator, that is a surrogate dynamical system, for predicting the future states of the time series. So to implement this method, you give yourself a kernel K, you use the past states of the dynamical system to construct input-output training data, then you interpolate that data with the kernel K to obtain an interpolant of the vector field F dagger. And finally, you simulate the following surrogate dynamical system to predict future states. And here, for the sake of time, I'm restricting the presentation to the case where the time delay to dagger is known. And I refer to this paper for how we learn it in practice. Okay, so how well does it work? Well, to answer that question, let us look at the following example, where the time series is produced by the solution of the Bernoulli map, which is a chaotic dynamical system, and the kernel K is the following Gaussian kernel. This figure shows in red the true dynamic, and in blue the predicted dynamic. So it does not work well. Well, now let us add a little twist to this experiment, and let us also learn the kernel K used for creating the surrogate model. What do I mean? Well, for that example, what I mean is that instead of considering a given kernel K, we consider a family of kernel Ks parameterized by 4 parameters. And we also learn those parameters from the data before regressing the target vector field F dagger. We learn them using the kernel flow algorithm, which I've already described. This figure shows the true dynamic in red and the predicted dynamic in blue. And they are indistinguishable in eyeball norm. Are you? Okay, now let us move on to another example. This example is the Houman map, i.e. in this example, the time series that we want to predict is a solution of the following dynamical system, which we assume to be unknown, and it is also chaotic. To predict it, we approximate its vector field by interpolating the past data with this vector-valued kernel. This kernel is diagonal, and each diagonal entry is a scalar-valued kernel with 6 parameters. And we learn those parameters using kernel flow. So we have 12 parameters to learn. The left figure shows the true unpredicted dynamic with the learned kernel. And again, there is no difference in eyeball norm. The right figure shows the prediction error with the initial kernel in red and with the learned kernel in blue. And as you can see, the error drops by several orders of magnitude. Let us now look at this other example in which the time series is 3-dimensional and the solution of the Lorentz dynamical system. Our vector-valued kernel is diagonal as before with the following diagonal entries. So it has 18 parameters to learn. And we learn those parameters with the kernel flow algorithm. And these figures show the true dynamic and predicted dynamic for the 3 components of the dynamical system. And as you can see, there is no difference between them in eyeball norm. This method is not limited to toy problems, and this joint work with Romit Molik from Argonne National Lab, who is also in the audience, we have used this method to extrapolate weather/time series obtained from satellite data. We have compared the proposed kernel-based method with 2 PDE-based methods, HiCom and CSM, and an architecture optimized LSTM method, which is an artificial neural network method. HiCom took 800 core hours per day of forecast on a Cray XC40 system. CSM took 17 million core hours on Yellowstone NCAR's high-performance computing resource. the architecture optimized LSTM took 3 hours of wall time on 128 compute nodes on the Theta supercomputer. Our simple kernel-based method took 40 seconds to train on a single node machine, a laptop without acceleration. For the NOAA dataset, which is a low noise dataset, our kernel-based method and the LSTM method have comparable accuracies. And these accuracies are significantly better than those of the PDE-based methods. For the NAM dataset, which is a high noise dataset, the LSTM method has poor accuracy, while our simple kernel-based method remains accurate. And I'm running out of time, so I will stop here, and I'm happy to take questions.
Thank you very much for the great talk.
Thank you.